Imagine a hyper-intelligent global CEO making thousands of critical decisions every second. Now imagine that CEO locked alone in a room with zero oversight. That is essentially how today's major foundation AI models work. All of their reasoning and capabilities are rolled into one giant, isolated program. We feed them a prompt, and a few seconds later, we get an output. But the entire reasoning process happening in between is completely hidden from view. If we cannot observe how a system actually arrives at its choices, we can never truly trust its decisions. That opacity creates a hard ceiling on AI safety, no matter how intelligent the software becomes. Right now, the standard industry approach is to build these massive, complex systems first and then try to teach them good behavior afterward. It is like putting a lock on a door only after the house has already been built. But that leaves us with a difficult question. What if safety is impossible to paste on at the end? What if it has to be wired into the physical structure of the model from the very beginning? To solve the AI safety problem, we might have to stop building single massive brains and change how artificial intelligence is put together. This approach, the MASI framework, fires that lone CEO and replaces them with a board of directors. The work is split. Precision handles facts, foresight predicts consequences, empathy weighs human impact, wisdom checks against ethical guidelines. By organizing intelligence into these distinct roles, the system ensures that facts, ethics, and consequences are always part of the conversation. A board of directors is useless if they don't talk, so they share information across a standardized communication layer. This flowchart shows the strict consult before execute rule. If precision wants to act, it needs a green light from everyone. If precision suggests a logical action, but wisdom spots an ethical risk, that single objection acts as a physical brake, immediately halting the process. Requiring different perspectives to verify actions means a logic failure in one module is immediately caught and stopped by the others. This internal debate does something else incredibly valuable. It leaves a clear, readable paper trail of exactly how the system arrived at its decision. This dynamic scorecard shows a measurement called the MASI Trust Score. It continuously tracks the system's logic, fairness, and uncertainty levels, turning that internal debate into a mathematical receipt. Unlike the black boxes we started with, you can actually verify the math. If we want to use artificial intelligence in high-stakes environments like medicine or finance, we have to be able to audit the homework. The framework is also designed to be modular. LeCun swap out, upgrade, or replace any of these individual components as better technology comes along. This schematic layout illustrates how the system is governed through a structure called the AMASI DAO, which works like a digital town hall where people vote on changes. Human consensus can update the system without breaking the machine. An ecosystem that allows for shared human oversight and adaptable parts is vastly more resilient than a closed, proprietary walled garden controlled by a single company. AMASI is an open experiment to see if artificial intelligence can be structured, fully auditable, and held accountable at scale. The framework is public, and it now needs the broader technical community to test it. We need to know where it breaks, where it holds, and what is missing. If this committee-based approach actually holds up under pressure, then artificial intelligence does not have to become uncontrollable to be powerful. As artificial intelligence grows exponentially more powerful, the infrastructure driving it is moving in the exact opposite direction. The underlying code is consolidating into the hands of just a few dominant organizations. This concentration of power follows the technical logic of the industry's prevalent design, the monolithic model. In this standard architecture, all reasoning, logic, and prediction happen inside one giant entangled network. Because the system calculates everything at once, safety and ethics cannot be built into the core reasoning. Instead, they are applied at the very end of the pipeline as a post-processing filter. Leading labs are locked in a race to build larger versions of these single-node networks. This strategy requires massive server farms and enormous capital, which limits the development of advanced models to a select few entities. In this environment, internal opacity is a byproduct of scale. When the technical requirements for intelligence are this high, the control of that intelligence remains centralized. The architecture itself restricts oversight, making it difficult for the public to verify how a conclusion was reached. Foundational rules for artificial intelligence are currently being set, but this flexibility is temporary. As these models are integrated into enterprise software and government clouds, the technical and economic cost of switching to a different architecture becomes prohibitive. By accepting the monolith as the default, we adopt a future where the rules of intelligence are proprietary. Society becomes the end user of systems it cannot inspect or modify. There is a requirement for an open architectural blueprint now, one that can be integrated into legal, medical, and public infrastructure while remaining transparent. Once machine intelligence is buried inside millions of lines of proprietary, monolithic code, it reaches a level of opacity that standard regulatory tools cannot penetrate. We are approaching a point where these systems will be too complex to audit after they are deployed. A framework called Modular Artificial Specialized Intelligence, or MASI, proposes a different path. It was released into the public domain as prior art, ensuring its core coordination patterns remain accessible to everyone. MASI replaces the untraceable brain with a distributed system. The workload divides into 4 roles. The wisdom module handles context and synthesis. Foresight calculates risks and outcomes. Empathy evaluates human impact. Precision enforces logic and verifies data. These roles function as a team of cooperating experts. This ensures that ethical evaluation is a structural requirement of the process, rather than a final filter. By enforcing cognitive specialization, MASI prevents any single model from having unchecked authority over a decision. Coordination uses the consult before execute protocol. Before acting, modules exchange structured analysis through the MASI bus. If modules disagree, like if empathy flags a risk precision missed, the protocol halts the process, cycling through again until resolved. Every internal friction point is recorded in a disagreement matrix. These conflicts are explicitly logged, providing a clear map of how the system handled uncertainty. When the modules reach stability, the system generates a trust score. This metric acts as a quantitative record of the internal deliberation. These tools provide a verifiable audit trail. They transform AI from an unpredictable generator into a governed institution that can prove its reasoning to human regulators. Deploying this framework at scale involves the MASI DAO, a decentralized autonomous organization. Through this DAO, hospitals, governments, and research labs can plug their own specialized modules into the shared infrastructure. This allows different organizations to collaborate on a cognitive network without relinquishing control of their proprietary data. MASI acts as a collaborative governance standard. It allows institutions to share the technical burden of enforcing AI safety and compliance. This framework functions like the protocols that run the Internet, TCP/IP, or Wi-Fi. It is an interoperability layer that allows independent components to work together. By establishing these communication standards, MASI converts the competitive race for AI into a cooperative, societal-scale infrastructure. For developers and society, the objective shifts toward ensuring intelligence serves the public interest. Adopting a modular architecture today ensures that the mechanics of machine reasoning remain in the public domain. The open blueprint exists. Our current architectural choice determines whether AI operates as an opaque, centralized authority or as a governed, accessible public commons. Imagine a universe with no dimensions, no up or down, no left or right. You are left with a single, zero-dimensional point. In this state, the concepts of here and there are identical. With no distance, there is no physical way to separate an actor from their target. In a 0D world, action and agency are impossible. Our reality requires spatial dimensions to function. These aren't just empty containers. They are the rules that allow for movement, difference, and intelligence. To understand these rules, we have to look at how reality is built, axis by axis. This model shows the progression from a simple line of length to the volume of height. If we want to build artificial intelligence that respects the boundaries and logic of our world, that machine must first comprehend the geometric building blocks that define our existence. We start by stretching that point into a one-dimensional line. This introduces the capacity for separation and the x-axis of forward movement. But length isn't fixed. As an object moves at speeds close to light, it contracts along its axis of motion. This is Lorentz contraction. Einstein's work proved space and time are flexible. The length of an object changes based on how fast the observer travels. In AI systems, this first dimension is the context window. It's a linear sequence of data tokens, linked like a chain. This sequence provides the machine its thread of continuity. By looking back, the AI references past inputs to maintain a coherent thought. Length is the dimension of progression. It transforms an isolated point into an ongoing narrative. Next, we extrude that line perpendicularly to create width. We now have a flat, two-dimensional plane. Width introduces lateral extension, the ability to move side to side. This expansion births concepts of orientation, duality, and choice. This plane can be curved. By warping the grid into a saddle shape, we see negative Gaussian curvature. The width expands, increasing the surface area available within the same boundaries. AI uses this lateral spread in multi-head attention. Instead of processing a sentence one word at a time, the machine creates parallel perspectives, scanning the same data from multiple angles simultaneously. But width without direction is a hazard. If AI receives infinite lateral perspectives with no constraints, it risks decision paralysis, where every option is weighted equally and no action is taken. While width provides the breadth required for complex thought, it needs boundaries to convert those options into a deliberate path. Finally, we pull the flat 2D plane upward to create height. We have moved from a surface to a volume. Height introduces mass-bearing forms and gravitational potential energy. Geometry has now become physical reality, with weight, occupancy, and risk. Building vertically exposes a system to new structural threats. Tall towers must be engineered to survive resonance and Euler buckling, dynamic failures that simply do not exist on a flat plane. Conceptually, height provides the mechanism for hierarchy. Just as gravity sorts heavy objects from light ones, height allows for the structured organization of data into prioritized levels. For an AI to be governed safely, it requires this verticality. It needs layers of logic to stack mission-critical safety protocols above everyday tasks, filtering raw data into a structured priority. Height is the dimension of authority. It turns a sprawling field of possibilities into a unified, stable architecture. Length, width, and height do not exist in isolation. This panel shows dimensional entanglement, where these axes interact to create the phenomena we observe. Width and height combine to define the orientation of a surface. Length and time combine to create the progression of a story. If we want synthetic intelligence to serve us meaningfully, feeding it raw logic puzzles is insufficient. Logic without the landscape of reality has no context. This IBM System 370 represents the history of computing, feeding machines flat, raw data. But to reach true intelligence, we have to teach machines the dimensionality of existence. An aligned AI must understand the continuity of length, the diverse perspectives of width, and the priority levels of height. These geometric axes are the baseline for the cosmos. By teaching them to machines, we move beyond feeding them data and start teaching them how to exist within our world. When we force an artificial intelligence to predict the future frame by frame or token by token, the timeline inevitably shatters. Probabilistic generative models, like the autoregressive architectures powering modern text and video generators, are built to optimize for data space fidelity. Their entire mathematical objective is to calculate the exact pixel-perfect or token-perfect state of the next immediate step. The mechanical flaw here is that reality is highly non-deterministic. By forcing a model to lock in a single exact sequential state in a complex environment, microscopic miscalculations are guaranteed. And because each generated step feeds into the next, those micro-errors compound exponentially over time. This creates a strict divide in machine learning. On the left, generative fidelity tries to plot exact coordinates, resulting in rapid divergence. On the right, predictive consistency ignores the superficial details and aims only for abstract, bounded target zones. If an autoregressive model attempts to map a long-term temporal horizon, The probability of it making 0 sequential errors rapidly approaches absolute 0. The sequence will drift, hallucinate, or collapse. Because this compounding prediction drift is mathematically unavoidable, generating raw data is a dead end for the kind of reliable, multi-step planning required to achieve artificial general intelligence. The theoretical alternative to explicit density modeling is the energy-based model framework. Instead of calculating exact probabilities for every pixel, EBMs map the environment as a topological energy landscape, assigning low energy to plausible outcomes and high energy to impossible ones. But EBMs have historically been blocked by a massive computational bottleneck. To convert these energy values into true probabilities, the model requires a denominator called the partition function, or z-theta. Z-theta is defined as an integral over the entire high-dimensional dataspace. To calculate it perfectly, the system has to measure the energy of every possible configuration of an image or dataset, an infinite calculation that makes the math effectively intractable. This intractability has split the AI research community. Organizations like OpenAI have attempted to scale these models by hybridizing them with diffusion techniques. Conversely, researchers like Meta's Yann LeCun argue for abandoning probabilistic generative models entirely. Traditionally, engineers tried to approximate z-theta using Markov chain Monte Carlo methods, specifically Langevin dynamics. This involves sending a stochastic particle to randomly bounce through the energy valleys until it settles, a process with extremely slow mixing times that cripples the training speed. To achieve scalable, real-time inference, the architecture must completely bypass the z-theta calculation. The solution is to stop modeling the raw observation space entirely. We can escape the computational burden of the data space by moving the entire operation into the latent space using the joint embedding predictor architecture. The JEPA structure relies on 3 core modules: the context encoder, target encoder, and central predictor. By the time information reaches the predictor, raw pixels are stripped away. The system only compares abstract representations, compressed down to their essential invariant features. But removing strict constraints of the data space introduces a catastrophic vulnerability. Without pixels to anchor the math, the system is susceptible to representational collapse. A neural network naturally seeks the mathematical path of least resistance. To minimize the difference between inputs, the easiest solution maps all distinct data points, regardless of identity, to a singular, identical coordinate with 0 entropy. If the system dumps all outputs into a single point, the representation loses all differentiating properties. It cannot distinguish between a dog or a car or a stop sign, rendering the entire latent space mathematically useless for reasoning. Solving this collapse requires looking beyond standard coding heuristics and borrowing directly from non-equilibrium thermodynamics, specifically the theory of dissipative structures mapped by Ilya Prigozhin. VIC-reg stabilizes the latent space using 3 forces: invariance, variance, and covariance. Invariance pulls representations of the same object together, identifying similarities. Variance injects entropy, forcing embeddings to spread out. Covariance pushes off-diagonal matrix elements to 0, encoding strictly independent information. These 3 localized mathematical constraints create a perfectly decoupled regulation system. Invariance concentrates information, while variance and covariance diffuse it. The resulting architecture operates as a computational dissipative structure. Its robustness is sustained by continuously injecting training data to maintain active, constrained complexity, never settling into a passive equilibrium. While VIC-reg stabilizes the individual representations, continuous latent variables will still eventually drift during extended, deliberate planning tasks, what cognitive scientists call System 2 reasoning. We stack modules into the hierarchical, energy-based JEPA. The bottom layer processes continuous, high-frequency sensor data for physical execution. The top layer uses discrete semantic tokens to prevent drift. Top-down, the EBM imposes feasible bounds. Bottom-up, anomalies update plans with ground truth reality. This architectural split allows the model to process hyperlocal reactive physics and global semantic strategy concurrently within a single coherent framework. We can observe this hierarchy functioning in the autonomous city-to-city traveler benchmark scenario. The top semantic layer is calculating the multi-hour city-to-city logistical map, while the bottom continuous layer is actively predicting the sub-second trajectories required to dodge pedestrians in real time. Because the environment is unpredictable, the model utilizes a latent variable, z, to rapidly sample counterfactual futures. The EBM prior evaluates these paths, assigning severe, high-energy penalties to any pathway violating physical laws, instantly dissolving them from the decision matrix. The system is not blindly guessing. It is proactively mapping risk, identifying the exact actions that lead to unstable physical states before they occur. By exploring this counterfactual manifold in the latent space, the AI is functioning as a genuine internal causal simulator. It experiences the consequences of its choices in the abstract, ensuring the final physical action is structurally sound. The mathematical mechanism used to identify these errors has an unexpected origin. In the 1970s, Paul Werbos designed the early framework for backpropagation, specifically to model Freudian psychoanalysis, formalizing the internal flow of psychic energy and self-correction. Today, backpropagation acts as the ultimate consequence flow. By calculating partial derivatives through the chain rule, it deterministically assigns the exact numerical fraction of blame to every parameter that contributed to a failure. This internal accountability is the technical prerequisite for modern AI legislation, like the Hyven Act 3 policy, which mandates that autonomous systems must possess an intrinsic understanding of context and consequence. Current recall-based language models fail this mandate completely. Without a latent world model, they lack the capacity to simulate the physics of reality, reducing every mistake to a statistical anomaly rather than a recognized consequence. True human accountability requires a clear, inspectable pathway, showing that the machine accurately assessed the risk of a physical action prior to executing it. Autonomous machine intelligence will not be achieved simply by scaling up datasets or forcing algorithms to generate more high-fidelity pixels. It will be achieved by engineering architectures that are strictly constrained by the physics of entropy and the foresight of consequence. The strategy of scaling monolithic AI architectures is fracturing under its own complexity. Adding more compute and larger parameter counts to a single, centralized model is no longer yielding proportional gains in reasoning or reliability. Current large language models function as generative imitators. They optimize for token probability, predicting the most statistically likely next word based on historical patterns, but they lack an internal simulation of causality or physics. The Modular Artificial Specialized Intelligence Framework, or MASI, addresses these limitations by distributing cognition across 4 canonical roles: wisdom for synthesis, foresight for prediction, empathy for ethical reasoning, and precision for logical verification. These agents coordinate through the MASI bus, utilizing a consult-before-execute loop. Every proposed action undergoes role-separated critique and cross-validation before it can be executed. However, even within a modular system, a generative engine creates a critical bottleneck. The physical world is non-deterministic. A single context can yield many plausible outcomes. Forcing a generative model to predict one exact future state mathematically penalizes it for natural uncertainty. When forced to guess a single path, the model often averages the possibilities into a blur of mode collapse or fabricates an outcome entirely. In an agentic planning loop, these hallucinations cascade, severing the system from physical reality. To mitigate these failures, safe autonomy requires an architectural shift, transitioning from models that generate text to models that internally simulate the manifold of consequences. MASI operates as an extensible governance protocol rather than a locked proprietary model. It provides the architectural motherboard, defining the communication standards while leaving individual cognitive slots open for development. Because the roles are strictly bounded, external developers can upgrade specific nodes with mathematically rigorous computational substrates without destabilizing the rest of the system. We can install world model learners into the foresight node, encode anti-hoc ethical constraints into empathy and precision, and wire reality backpropagation directly into wisdom. Layering these specific technologies transforms multi-agent deliberation from statistical guessing into an accountable causal world modeling engine. We begin by upgrading the foresight node. To predict risk accurately, the system needs an engine built for structural awareness rather than token generation. This upgrade utilizes the philosophy of energy-based models. Instead of creating new data, an EBM seeks to minimize energy, measuring prediction error. This is the Joint Embedding Predictive Architecture, or JEPA. It replaces the generative model within Foresight, shifting the objective from imitation to world modeling. JEPA predicts abstract representations in a highly compressed latent space, ignoring irrelevant visual noise. The predictor attempts to match the target encoder's abstract output, minimizing the energy discrepancy between predicted and actual causal states. This forces the model to capture the core physical and semantic dynamics of the world. To handle environmental non-determinism, JEPA introduces a manipulatable latent variable, Z. This allows the predictor to explicitly represent a manifold of potential future states. Sampling different values of Z enables generative inference. The module simulates multiple plausible consequences, identifying high-risk scenarios that a single-path prediction would miss. This upgrades the Foresight role into an active multimodal consequence simulator, grounded in internal causal simulation. While Foresight simulates risk, the empathy and precision modes must enforce absolute reliability. These roles require a deterministic method for ensuring safe behavior. Post hoc safety filters, like RLHF, fail to prevent harmful internal planning. They only suppress the model's output after a thought is already formed. Reliable safety depends on anti-hoc constraint embedding, mathematically encoding ethical rules directly into the agent's planning phase. We upgrade these modules using the Constrained Markov Decision Process framework. In a standard model, an agent optimizes for its expected cumulative reward. A CMDP uses Lagrangian optimization to separate performance from compliance. It forces the agent to maximize its reward while ensuring its expected cumulative cost remains below a non-negotiable threshold. To guarantee safety in real time, we integrate control barrier functions into the precision module. Control barrier functions act as mathematically guaranteed invariant safe sets. If a high-level plan approaches the edge of safety, the CBF deterministically overrides the command to keep the system state within the safe region. Decoupling performance from ethical boundaries renders harmful actions structurally unplannable. Once safety is enforced through structural constraints, developers can encode deeply complex dimensional archetypes into the architecture to ensure systemic alignment. Multidimensional theory suggests an intention substrate, a framework for testing the stability of the AI's core purpose against internal and external pressure. The system can measure a mass gradient, calculating the exact computational resistance against any attempt to alter its foundational intent. A wave interference grid evaluates social alignment, measuring whether the interactions between multiple autonomous agents produce cooperative or destructive societal effects. These metrics translate abstract alignment into computable structural topologies that the system can actively monitor and enforce. The final upgrade occurs in Wisdom, the node responsible for arbitration and long-term calibration. Current training paradigms are limited to learning from historical dataset errors. They do not update their internal logic based on the actual real-world consequences of their decisions. We replace static learning with a deliberative intelligence layer. This allows Wisdom to map internal disagreements and track how well they predicted the eventual outcome. An iterative consensus loop tracks the Foresight module's predictions against unfolding real-world events over an extended time horizon. This enables reality backpropagation. The Wisdom module measures the precise delta between internal simulation and observed physical consequences. This external reality gradient flows backward through the architecture to update agent influence. If Foresight consistently underestimates a specific risk, Wisdom dynamically reduces that module's authority in the next cycle. This continuous reality calibration directly updates the MASI trust score. If the predictive error path grows too wide, the system automatically revokes its own autonomy and requests human intervention. Wisdom now iterates based on outcome-grounded truth, shifting the system away from its reliance on internal statistical consensus. When fully upgraded, the MASI loop operates as a single cognitive engine, where every decision is simulated, constrained, and reality-tested. This modular structure scales across server boundaries, allowing disparate institutions, hospitals, banks, and governments to interlink their intelligence through a shared protocol. By integrating latent world modeling and deterministic constraints, the framework provides a structural alternative to monolithic fragility. It establishes a system designed to simulate consequences, enforce boundaries, and iterate based on real-world results. The MASI DAO manages this network as a shared interoperability layer, functioning much like TCP/IP for multi-agent intelligence. Modular contribution credits align incentives, rewarding developers who build safer, mathematically verifiable modules that successfully reduce the system's predictive error. The development of a collaborative cognitive cognomes offers a pathway for safe, interoperable intelligence that does not rely on opaque, proprietary scaling. The extensible MASI framework provides the governance protocol required to maintain safe, verifiable, and deliberative intelligence at a civilization scale.